Hello, guys. This is chapter 5. We are going to talk about integration today. We are in group 1, and our group have Qi Liang, Mingqi Zhou, Weichen Huang, Joyce, and Emma.
In this presentation, we are going to talk about the definition of integration and integral and limit, and techniques of integration, in which there are basic integral, identities, use substitution, integration by parts, trigonometric substitution, partial fraction, completing squares, eliminating roots, eliminating sine and cosine.
We already learned that differentiation is to find the slope of a function at a certain point. But today we are going to talk about integration, which is to find an area under a function in a certain range.
Let's find out how to find the area of under a function within a certain range. An example that we're going to examine here is the function y equals to root of x from x equal to 0 to x equal to 1. The first step we are going to take is find the delta x, which is the base of these green rectangles that we're going to find the area of. And the delta x can be found by the formula the endpoint of the range minus the beginning of the range divided by a certain number of partition. Now the second step, after we found the delta x, we can start finding the boundaries. We are going to write the boundaries using the symbol xi, which is x and an indicator number, and the x of the indicator number will be 0 plus indicator number times delta x. The third step, we have to find the f of xi. In this case, it will be root of xi. When I equals to 1, the f of xi will be root of x1. If I equals to 2, f of xi will equal to root of x2, etc. and etc. Now that we have established the base and the height of each rectangle, we can start finding the area of the rectangle. As we can see, delta x will be the base of the rectangle and f of xi will be the height of one rectangle. So let's find out what the area is. Because an area of a rectangle is the length of its base times the length of its height, area for one rectangle here under this function will equal to delta x times f of x. And we know from earlier that delta x equals to 1 over n, and f of xi equals to root of xi. Therefore, the area will equal to 1 over n times root of xi. After finding out this, we can move on to the next step, which is step 5. We have to sum all of the areas of all the rectangles from within this range. And the areas will be 1 over n times x1 plus 1 over n times root of x2, etc. and etc. And if we compile them and write them in a certain notation, we can use the sigma notation to write it as 1 over n times sigma of root of xi from I equals to 1 to I equals to I. Next step, because we know that by only doing a certain number of partition, the error is going to be high. We know this error because there are still some areas left that are not counted by the area of the rectangles, which is why we have to increase the number of partition so that the error becomes less and less. And ideally, we want unlimited number of partition or infinity number of partition so that the area is so close to 0 that it can be ignored. So we are going to rewrite the entire formula in terms using a limit form so that we can increase the number of partition to infinity. And we do this by writing this as limit as n goes to infinity of 1 over n times sigma of root of xi from I equal to 1 to I equal to I. This is a picture representation of what I said in the previous slide. So if we only have a small number of partition, as we can see in the first graph here on the top left of the picture with the blue rectangles, the error is very high because it only used 4 partitions. But as we increase the number of partition, we can see the amount of error is going to decrease and decrease even more. Okay, so back to the previous formula. In the previous formula, we rewrite the entire formula of area under a graph into limit as n goes to infinity, but we know that 1 over n, which was in the previous formula, equals to delta x. Therefore, we can write the entire formula into this form. Limit of delta x times sigma of root of xi from I equals to 1 to I equals to I as delta x goes to 0. And this is the same formula to find area under a function. After that, we can rewrite this entire formula again using the integral signs. In Math 1a, we already learned that dx equals to limit of delta x as delta x goes to 0. So we can rewrite limit of delta x as delta x goes to 0 into dx. And then we can rewrite limit as delta x goes to 0 of sigma from I equal to 1 to I equal to I into just a basic integral form. And then we can rewrite root of xi into f of x, because in the previous function that we were analyzing, fx equals to root of x. As it turns out, integration is an inverse function of differentiation. Therefore, because we already learned several basic differentiation in the previous chapter, in the previous math class, we can now derive basic integrals based on those differentiation results. For example, we know that the differentiation of x to the power of n equals to n times x to the power of n minus 1. Therefore, we know that the integration of x to the power of n is x to the power of n plus 1 divided by n plus 1 plus c, because we know that a constant, when x function plus a constant is differentiated, this constant is going to become 0. Therefore, an integration of anything will go with a certain constant that we don't know what that is, which is why we are calling it c. And that also goes with all of the differentiation results. For example, cosine function, when it's differentiated, it becomes minus sine. Therefore, when we integrate sine x, it becomes minus cosine of x, because we know that when we differentiate minus of cosine of x, we will get sine of x. And of course, do not forget the plus c. And that goes for everything. And this is a table of basic integrals and differentiations that we have already set up for you. Please take a few minutes to look at this. The second technique that I am going to discuss here is the trigonometric identities. So there are several identities that we need to remember. For sinusoidal identities, we have sine square x plus cosine square x equals to 1, secant square x minus tangent square x equals to 1, cosine 2x equals to cosine square x minus sine square x. Therefore, 2 cosine square x minus 1 equal to 1 minus 2 sine square x. Therefore, sine square x equals to 1 minus cosine 2x over 2, and cosine 2x equals to 1 plus cosine 2x over 2. And sine 2x equals to 2 sine x cosine x. For hyperbolic identities, we need to remember that cosine hyperbolic square of x minus sine hyperbolic square of x equals to 1, and tangent hyperbolic square of x plus secant hyperbolic square of x equals to 1. And cosine 2 hyperbolic of 2x equals to cosine hyperbolic square of x plus sine hyperbolic square of x. Therefore, sine hyperbolic square of x equals to minus 1 plus cosine hyperbolic of 2x over 2. And cosine hyperbolic square of x equals to 1 plus cosine hyperbolic 2x over 2. Sine hyperbolic 2 of x equals to 2 sine hyperbolic x cosine hyperbolic x. These identities would be really useful for us to use in solving integration problems. For example, problems such as the integration of tangent of x. We have to change the tangent of x into sine x over cosine x. And integration of cosine square of x, we have to change cosine square of x into 1 plus cosine 2x over 2 to make the integration a lot easier. The third technique that we are going to discuss here is the u substitution technique. In u substitution technique, we simply use u to substitute a complicated function. After that, we can integrate the entire integration function in terms of u and that makes it a lot simpler. Let's look at several examples. For example, integration of 2 e to the power of 2x dx. Now let 2x equals to u and 2 dx equals to du. Therefore, we can change the function integral of 2 e to the power of 2x dx into integral of e to the power of u du. And we know that when we integrate e to the power of u plus c, we get e to the power of u. Therefore, the integration of e to the power of u in terms of du equals to e to the power of u plus c. And of course, we have to substitute back 2x equal to u, and it becomes e to the power of 2x plus c. Another example we have here is integration of 2x divided by root of x squared minus 1 dx. Let's let x squared minus 1 equals to u, so 2x dx equals to du. After changing everything and substituting into the function, we get integral of du over root of u. And that becomes a basic integration, and the answer to that is 2u to the power of 1/2 plus c. And we can change the u back into x squared minus 1, and we get 2 times root of x squared minus 1 plus c. The next thing that we are going to discuss is the technique of integration by parts. First, we have to look at where it came from. As you can remember in 1a, when solving a differentiation of a product, we have a product rule. Therefore, duv equals to udv plus vdu. We can then move vdu into the other side of the equation, and it becomes udv equals to d of uv minus vdu. And then we integrate both sides, and we get integration of udv equals to integration of duv minus integration of vdu. And integration of duv equals to uv. Therefore, integration of udv equals to uv minus integration of vdu. While using integration by parts to solve a certain problem, we have to be aware of the rank order for choosing u. The first one in the order is inverse function, the second one is polynomials, the third one is exponential and sinusoidal, and the last one is dx. How do we use this order? So for example, if we see a problem that has an inverse function in it and polynomials, we know that we have to let the inverse functions equal to u and the polynomials dx equals to dv. If we see a polynomials only and a dx, then we have to let the polynomials equals to u and the dx equals to du, etc. and etc. Now let's take a look for several example problems to make it clearer. We have here integration of x sine x dx. Now let's let u equals to x because x is a polynomial and sine is a sinusoidal terms. Therefore x is higher in the hierarchy. Therefore u equals to x and sine x dx equals to dv, and du equals to dx, while v equals to minus cosine of x. And we know that integration of u dv equals to uv, which in here equals to x times minus cosine x, which equals to minus x cosine x, minus integration of v du, which in here is integration of minus cosine x times dx. So it becomes minus cosine of x times x plus integration of cosine x dx. And integration of cosine x dx equals to sine x plus c. Therefore, the entire problem becomes minus x cosine x plus sine x plus c. A second example that we are going to do here is the integration of x times sine inverse of x dx. In here, we see that there is an inverse function and therefore is in the highest key. Therefore, we choose inverse function as the u. So let u equals to sine inverse of x and dv equals to x dx. Du equals to dx over root of 1 minus x squared, and v equals to half of x squared. And uv minus integral of v du equals to half of x squared times sine inverse of x minus integral of half of x squared times 1 over root of 1 minus x squared dx. The next technique that we are going to discuss here is trigonometric substitution. Basing off of the u substitution method, we can convert two terms into one term. For example, a squared minus x squared, or root of a squared minus x squared, or 1 over a squared minus x squared, or 1 over root of a squared minus x squared. We can let x equals to a sine theta or a cosine theta, and dx will become a cosine theta d theta or minus a sine theta d theta. And then a squared minus x squared will become a squared times 1 minus sine squared theta, or a squared times 1 minus cosine squared theta. And the entire thing will become a squared cosine squared theta, or a squared sine squared theta. And after that, we can do the same thing as u substitution and then substitute back theta into a squared minus x squared. The second type of trigonometric substitution that we're going to discuss is the form of a squared plus x squared. If in a problem you see a squared plus x squared in any form, in roots or in 1 over something, in 1 over root of something, you can let x equal to a tangent theta, so that a squared plus x squared becomes a squared times 1 plus tangent square theta, and it becomes a squared secant square x. And dx will equal to a secant square theta d theta. The type 3 of trigonometric substitution is if you see x squared minus a squared. If you see this form, you can you can let x equals to a secant theta, and so dx equals to a secant theta tangent theta d theta, and x squared minus a squared equals to a squared times secant square theta minus 1, and x squared minus a squared becomes a squared times tangent square theta. Let's look at an example. For type 1, the example that we're taking here is integration of root of 1 minus x squared dx. Here we see the form of a squared minus x squared, a squared being 1 and x squared being x squared. So we have to let x equal to sine theta, and therefore dx equals to cosine theta d theta. And integration of root of 1 minus x squared dx will become integration of root of cosine squared theta times cosine theta d theta. And it becomes integration of cosine squared theta d theta. After that, we have to use integration by using trigonometric identity. As I said before, if we find cosine square theta, we have to change it in the form of 1 plus cosine 2 theta divided by 2. And so the integration becomes integration of 1/2 plus 1/2 of cosine 2 theta d theta. And after we integrate it, we get half of theta minus 1/4 of sine 2 theta plus c. Now we have to convert theta in terms of x. Because we let x equals to sine theta, we get the triangle that is shown here with one of its side as x and its diagonal side as 1, and the angle right across from x equals to theta. And from there we can convert cosine theta, sine theta, tangent theta, secant theta, or any sinusoidal terms in terms of x. For this problem, we have 1/2 of theta, which is the sine inverse of x, so we can write it as half of sine inverse of x. And we have 1/4 of sine 2 theta, which we can change into 1/4 of sine theta cosine theta. And cosine theta here is root of 1 minus x squared, so the entire term becomes 1/4 of sine 1/4 of x times root of 1 minus x squared times 2, which becomes 1/2 of x times 1 minus x squared. And the entire thing still have c, so plus c. The second example that we are going to discuss is for the type 2. So here we have integral of 1 over 4 plus x squared dx. Now, because we see the form of a squared plus x squared, we can let x equals to 2 tangent theta. And dx will equal to 2 secant square theta d theta. Therefore, integral of 1 over 4 plus x squared, integral of 2 secant square 2 secant squared theta d theta over 4 secant square theta. And this entire thing will equal to integral of 1/2 d theta, and will equal to 1/2 theta. Then we can change theta back into tangent, and because x equals to 2 tangent theta, we know that half of theta equals to half of tangent inverse of x over 2. The third example that we are going to do here is for type 3, and the problem is integration of 1 over x times root of x squared minus 1 dx. In this question, because we see x squared minus a squared, we have to let x equals to secant of theta, and dx equals to secant theta tangent theta d theta. And integration of 1 over x times root of x squared minus 1 dx becomes integration of secant theta tangent theta over secant theta tangent theta times d theta, and it becomes integration of d theta and becomes theta. Therefore, after we change theta in terms of x, we get secant inverse of x plus c. The next technique that we are going to discuss here is partial fraction. It's to divide an original function into several basic functions, but it only works with fractions. For example, 1 over 1 minus x squared, we can convert it into 1 over 1 minus x times 1 plus x. Therefore, we can change it into a form that is a over 1 minus x plus b over 1 plus x. Because when we try to add these two fractions, we have to multiply the bottom, and the bottom will become 1 minus x squared. Therefore, we only have to make sure that a times 1 plus x plus b times 1 minus x equals to 1. Therefore, we get a system of equation which is a minus b equals to 0 and a plus b equals to 1. From here, we know that a equals to half and b equals to half too. Let's do an example. In this example, we choose a problem which is x plus 1 over x plus 1 times x minus 1. Then we divide them into a over x plus 2 plus b over x minus 1, in which a times x minus 1 plus b times x plus 2 equals 2x plus 1. Therefore, 2b minus a equals to 1 and a plus b equals to 1. From here, we know that a equals to 1 over 3 and b equals to 2 over 3. And we get the equation 1 over 3 over x plus 2 plus 2 over 3 over x minus 1. The next technique that we are going to discuss is completing the squares, in which we complete an original function into a perfect square function so that we can solve it with another method, mostly trigonometric substitution, but we can sometimes also use partial fraction. For example, for the integration of dx over 6x minus x squared, we can change it into minus sign or negative of integration of dx over x squared minus 6x plus something minus something. For a quadratic function ax squared plus bx plus c, we can change it into a times x plus something square plus c, and the missing number is b over 2a. Therefore, the previous function, we can change it into the negative of integral of dx over x squared minus 6x plus the b over 2a minus b over 2a. And b over 2a in this equation equals to 9, so we can change it into negative of integral of dx over x minus 3 square minus 9. And that equals to negative 1 over 9 times integral of dx over x minus 3 over 3 square minus 1. And here we can use trigonometric substitution to find a value of x, which makes the denominator become secant square x minus 1. Then the integral can be solved. To let it equal to secant square theta minus 1, we have to let x minus 3 over 3 equals to secant theta, and therefore 1/3 of dx equals to secant theta tangent theta d theta. And the function integral, the problem integral of dx over 6x minus x squared will become negative 1/9 times 3 of integral of 1/3 dx over x minus 3 over 3 square minus 1, and that equals to negative 1/3 integral of secant theta tangent theta d theta divided by secant theta square minus 1, and secant square theta minus 1 equals to tangent square theta, and therefore this entire problem becomes negative 1/3 times integral of secant theta divided by tangent theta d theta, and secant theta divided by tangent theta d theta becomes cosecant theta d theta, and we know that the integral of cosecant theta d theta equals to ln of cosecant theta plus cotangent theta times -1. Therefore, this problem becomes 1/3 times ln of absolute value of cosecant theta plus cotangent theta plus c. Then we still have to change cosecant theta and cotangent theta in terms of x. We come back and use the triangle method to find out what cosecant theta is or what cotangent theta is in terms of x, and we get, after doing some algebra, we get 1/3 of ln of x over x minus 6 plus c. The next method that we are going to discuss here is eliminating roots. Use u to cancel the radical in integrand to simplify the original function. For example, for the problem integral of 1/√3 of x plus 1, we let u cubed equals to x, and therefore 3u squared du equals to dx. And then we substitute in, so it becomes integral of 3u squared du over the √3 of u cubed is u, so it becomes u plus 1. And we can move the 3 out of the integral sign, so it becomes 3 times integral of u squared minus 1 plus 1 over u plus 1, and du times du, and that equals to 3 times integral of u minus 1 plus 1 over u plus 1 du. After doing some algebra and basic integrations, we get the result of 3/2 x to the power of 2/3 minus 3√3 of x plus 3 ln √3 of x plus 1. The next method that we are going to discuss is eliminating sine or cosine. To convert sine functions into a regular function. In order to do this method, we have to start with tangent x over 2 equals to u. We have to let this happen so that 1/2 of secant square x dx equals to du, and dx equals to 2 du over u squared plus 1. And sine x, because we know that sine x equals to 2 sine x over 2 cosine x over 2, we can change these into 2u over root of u squared plus 1 times 1 over u squared plus 1, which equals to 2u over u squared plus 1. Cosine x, because we know that cosine x equals to cosine square x over 2 minus sine square x over 2, we can change this in terms of u to become 1 over u squared plus 1 minus u squared over u squared plus 1, which becomes 1 minus u squared over 1 plus u squared. Let's take a look at an example. The example that we choose is integral of dx over sine x plus cosine x. Now, after substituting sine x into 2u over 1 plus u squared and cosine x into 1 minus u squared over 1 plus u squared and dx equal to 2 du over 1 plus u squared and tangent x over 2 equals to u, we get integral of 2 du over 2 minus u minus 1 square. Now let's let u minus 1 equals to dz equals to c, so dz equals to du, and we get integral of 2 dc over 2 minus z square. Now let's let z equals to root 2 sine theta and dz equals to root 2 cosine theta d theta. And it becomes integral of 2 times root 2 cosine theta d theta over 2 minus 2 sine squared theta, and the entire thing becomes root 2 of ln secant theta plus tangent theta plus c, which equals to root 2 of ln of tangent x over 2 minus 1 plus root 2 over root of 2 minus tangent x over 2 minus 1 square, all in an absolute value, plus c. Now, let's look at several practice questions. Let's look at the one on the left. So it's integral of ln of absolute value of x and the entire thing squared dx. Here, we just use substitution to change ln x, absolute value of x, into c, and then do the entire thing using some algebra and basic integration. And then at some point, we do some integration by parts and we get the answer. Of course, we have to change the terms back in terms of x in order to get the final answer. Now let's look at the one on the right. We have sine 5x cosine 2x dx and the integral of that. Here we just simply use integration by parts. It's a little bit complicated and we have to do a lot of algebra and do the integration by parts several times, but that's all we do and we can get the answer after that. Let's look at another examples of practice question. The one on the left, we have integral of sine of ln of x dx. Again, we use substitution to change ln x in terms of du, and then we use integration by parts. We use integration by parts again, and then we get the answer. And of course, we have to remember to change everything back in terms of x. On the right here, we have a pretty complicated question. In this one, we separated the entire function into two fractions and then use u substitution to let secant inverse of x into u, and the equation becomes a lot simpler and we get the answer of minus 1/2 of cosecant inverse of x squared plus e to the power of secant inverse of x plus c. In these examples, on the left one, we still use some kind of u substitution, and while on the right side, we use trigonometric substitution. And in both cases, we get the same answer. Even if we got a different answer at first on the right side, we can still change that answer into the same answer of the left side. it means that the answer must be right. Let's look at yet another example. In the left, we only use basic u substitution method, and then we change everything in terms of u and did some basic integration, and we got the answer. On the right, we times the entire thing by 2 and then time it again by half, so we don't change anything, and then we added the numerator with cosine x and minus it with another cosine x. Therefore, we can change it into sine x plus cosine x over sine x plus cosine x plus sine x minus cosine x over sine x plus cosine x, and we get a really simple integration. We just have to use u substitution for the more complicated part, and we get the answer. Now let's look at this example. We have to use limits this time because when t equals to 0, the denominator becomes 0, and that is undefined, and when t equals to 1, the denominator becomes 0 too, so it becomes undefined too. So we have to add limit to this entire problem, and it becomes limit of as a goes to 1 and b goes to 0 of integration of from b to a of 1 over t times root of 1 minus t squared dt. And then we can do it normally. We can use trigonometric substitution for this, and it becomes a really simple equation, and we get the answer right there. Right part of the practice, use Leibniz rule to differentiate the following integral. So right here, right under Leibniz rule, we have the proof of Leibniz rule and what that is. So it's basically a rule of the rate of change of an area of a function if their limits are changing. And then after using that rule, we get the answer, which is shown in the bottom of the slide. For this problem on the left here, we separated the function on the top so that it can be divisible by the denominator, and then separated the entire fraction into two fractions. And so the one on the left, we don't have to worry about that anymore because that is a basic integration, while the one on the right, we still need to do something about that, and we use partial fraction to change it into two different equations yet again. And then we use a bit of u substitution for the first part of the partial fraction and use trigonometric substitution for the right part of the equation, and then we get the answer. For the right part of the practice problem, we have integral of dx over e to the power of x times 1 plus 2 e to the power of x. For this one, we definitely have to use partial fraction. And we know that a equals to 1 and b equals to minus 2. Therefore, it becomes the integral of 1 over e to the power of x minus 2 over 1 plus 2 e to the power of x dx, and then that is just a basic integral, and we get the answer right there. For the left part of this practice problem, we use complete the square and then use trigonometric substitution, and then it becomes a pretty simple problem because it becomes that, and we find the solution right there. For the right part of the practice problem, we have the problem integral of x over root of x squared minus 4x dx. And still we use complete the square and then we substitute using trigonometric substitution, and then we separate them into several different fractions and we get the answer. Okay, so that was the last problem that we have for you, and this is the end of our presentation. Thank you for listening.